So we have defined an interval. So if the 2 points that we are measuring the intervals for, if they're very close to each other, then we can write the interval as an infinitesimal interval. So this is the notation that we use if the 2 points are very close to each other. And then the expression is given by c squared dt squared minus dx squared dy squared minus dz squared. So this is the infinitesimal interval. This is also called the line element sometimes. Now, it's kind of inconvenient to carry around this factor of c all around. So in high energy physics and quantum field theory, we use units in which the value of c is set to 1. So this is the units that we use. So how does this work? So suppose that, we have measured some length, say L, in this unit. So how do we convert it to the more familiar units? So what it means that this length L is the distance that it's measured in units of distance that light travels in 1 unit of time. So for example, if I take that unit of time to be the unit of time in MKS, so if I take that unit of time to be, say, 1 second, then this length will become L times what is the distance that light travels in 1 second? It's roughly 3 into 10 to the power 8 meters. So this is how we convert length measured in c equals to 1 unit to our familiar MKS unit. Similarly, suppose that we have measured some time t in our c equals to 1 unit. To convert it to our MK unit, what we have to do is that we have to look at the time that it takes for light to travel 1 unit distance. So in the MK unit, units, that's 1 meter. So the time is going to be 3 times 10 to the power minus 8. So then in MKS unit, this t will convert to 3 into 3 into 10 to the power minus 8 seconds. So this is how we convert between the c equals to 1 units. This is also called the natural units. Pretty soon we will also include the value of h bar will be 1 as well, but we will get to that. So if I do that, then this expression for the interval is going to be just dt squared minus, say, dx squared, where this is just dx dot dx, the usual dot product in 3 dimensions. So let's now discuss the idea of an invariant interval. So the invariant interval is actually the same thing as our interval, but let us prove that. So we have some, say, 2 points which are close to each other, and the interval between them is ds in one reference frame, say in the S reference frame. Say in the S prime reference frame, the interval is ds prime. So of course, these two are related by some transformation. So we saw that they are equal and 0 for 2 points, two events which are separated by a light-like interval. So ds will be a function of ds prime. So that means we can express ds as the derivative of, the derivative with respect to s prime times ds prime. Or in other words, we can call this ds is equal to some constant a times ds prime. This is consistent with 2 points when they are like separated. If 1 and 2 are like separated, we saw that ds is equal to ds prime is equal to 0. So that is consistent with this relationship. But what if the 2 points are not like separated, but some general separation? What is the value of a in that case? So, let's assume that, let's take 3 inertial reference frame, S prime, and S double prime. And let's suppose that we go from S to S prime by that S prime is traveling with respect to S with some velocity, say V prime. And S is, or actually let's call this, instead of primes, let's call it S, S1, and S2. And so the reference frame S1 is traveling with respect to S with a velocity V1, and similarly S2 is respect to S is traveling with the velocity S2, and then S1 and S2 are related by some relative velocity V12. Of course, if we know V1 and V2, we could express that V12 in terms of V1 and V2. So now let's write the line element that is the line elements in S and S1. So then it will be given by, so ds is going to be a, and it's a function of v1 and ds1. And similarly, this will be ds will be related to a v2 ds2. Before we move forward, I want to discuss the assumptions that we have about space-time. And the assumptions are that space-time is homogeneous, which means that every point in space-time is equivalent to every other point. This means that the physics should not depend on where we are doing our experiments or when we are doing experiments. The other thing that we are also assuming is that space-time is isotropic. And that means that all directions are the same. That is, if we do some experiment which involves some particular direction, say a reference frame moving in a particular direction, the physics in that reference frame should be equivalent to physics in any other reference frame moving in any other direction, provided that they're both inertial reference frames. So these are assumptions that we have. Because of this assumption, we have to, what we can conclude is that this constant A cannot depend on individual space-time points. So it cannot depend on the coordinates of the events here or here. And the other thing it cannot depend is the direction. So because it cannot depend on the direction, the constant A can only depend on the modulus or the magnitude of V. So, if you assume these things, then we can say that d of S1 is related to those of d of S2, the interval through A depending on V1, 2. But we know that the magnitude of this vector, V1, 2, depends on the angle between this vector and this vector. In other words, it depends on the directions of these vectors. Therefore, although these guys do not depend on any direction, this thing depends implicitly on the direction of V1 and V2. So now from these equations, what we can write is that we can take the ratio of ds1 and ds2. So we say, what is ds1 over ds2. So from these equation, what we get is that it's going to be a times a of v2 divided by a of v1. But from this thing, we see that this is equal to a of v12. So if I look at this equation, we see that the left-hand side doesn't depend on any direction where the right-hand side does. So this is a contradiction. This is a contradiction unless A actually is independent of V. That is, A is some constant. And if A is some constant, then this equation gives us the value of A as well. The value of A then is 1. Or in other words, we have proved in general that ds is equal to ds prime independent of whether the 2 points, the interval that we are looking at is light-like or not. Of course, this is also means that S12 is equal to S prime of 1, 2. So because this interval does not depend on the reference frame, this interval is called the invariant interval.